What do you picture when you think of a robot? Science fiction and recent developments in automation probably forms the basis of what you picture. Whether it's exploring the surface of Mars, assembling pieces of cars, or sent from the future to terminate you, all these robots, at their core, are very similar machines. They are all constructed with rigid metallic frames. They are all usually expensive to produce, requiring very specialized parts to function. They also all require complicated mathematical calculations to operate and cannot adapt to new situations without advanced artificial intelligence. In this video, I will investigate a new form of robotics, called soft robotics, which could enable the effective use of robots that are cheap to produce and do not require enormous computational power to operate flexibly. Imagine that I'm a robot, and you want me to pick up this apple and place it in this box without bruising or cutting the apple. For the sake of the demonstration, I will be using chopsticks as my robotic grabbers. Now, in order for me to grab this as a traditional hard robot, I need to know the exact location of the apple and the perfect points on the apple to grab onto. I would also need to know exactly how much force to apply to pick up the apple. Too little and the apple slips. Too much and the apple will be damaged. Say I did decide to work out all the math necessary to code the perfect path for my robotic grabbers and calculate the perfect amount of force to apply to pick up this apple. Great, you say. We have a robot ready to grab apples along a conveyor belt. Not quite. If I needed to pick up different apples at different positions, most of the math I used to pick up the first apple wouldn't be any use to me. I need something that can grab the apple just as easily as I can grab it with my hands. Soft robots attempt to mimic the functionality of muscles, taking a lot of their inspiration from animals like the octopus, which can move with strength and flexibility without a skeletal structure. The robot consists of a membrane filled with air or a liquid. The pressure inside the membrane can be controlled with an electronic pump. Through the expansion and contraction of the membrane, the motion of the soft robot can be controlled easily. The function of the soft robot is determined by its structure. They can be made to extend, twist, buckle, and curl in a near infinite number of combinations based only on how the membrane is constructed. And the algorithms exist to tell us exactly how to fold a membrane so that the robot moves exactly how we want it to. This is one of the great strengths of soft robots. Where a traditional robot would need intricate wiring and mathematical calculations to coordinate such complicated movements, a soft robot can operate effectively with only the pressure needing to be controlled. Soft Robotics Incorporated is a company seeking to introduce this technology into mainstream industry. They produce grabber attachments made with soft fluidic actuators for existing conveyor belt robot arms. The actuators of the grabber deform easily to fit the shape of the object it wishes to pick up. Because the force from the grabber is evenly distributed across the contact surface, there is a low risk of damaging the object when it is grabbed. This technology has a lot of potential to work in the agriculture industry, as a soft robot can just as easily pick fruit from a tree as it can from a conveyor belt. Harvard University's Biodesign Lab is working on applying the technology of soft robots to the field of medicine and rehabilitation. The team at Harvard is developing a glove with soft fluidic actuators that mimic the motion of a hand. The hope is to assist patients who have lost hand motor control through a stroke or other disease. If successful, this device could return independence to millions of chronic patients and allow them to perform many necessary daily activities.
I have only touched on a few of the many ways that soft robotics can be used to improve the world. As an alternative to robots with rigid metallic structures, they are effective in areas where a gentler touch is needed, such as food handling and medicine. They also open the door to the possibility of creating robots that can work side by side with human workers without putting human lives at risk. Soft robots are cheaper, easier to produce, and less fragile than their metallic cousins, but they are not a replacement for traditional robots. While soft robots can be built to accomplish a wide assortment of tasks, current actuators are only built to operate from a low-pressure state to a high-pressure state. This limits the number of tasks a single soft robot can do, while a traditional robot could be reprogrammed to complete a number of different operations without altering its hardware. Ideally, I believe the future of robotics is one where new soft robotics and traditional hard robotics are integrated together effectively to create a better machine, one that will be able to help us solve many problems facing humanity today and in our future.